4 answers, 1 obvious serverless choice, until you read the last line of the scenario. The job runs for 20 minutes. That single number quietly disqualifies the option everyone reaches for first, because one of these services has a hard ceiling at 15 minutes and cannot go a second past it. Welcome to episode 24 of Cloud Architect Path. By the end of this video, you'll be able to pick the right compute service from the shape of the workload alone and know exactly when a constraint like that 15-minute wall overrules the easy answer. This sits in both the performance and the cost domains of the Solutions Architect Associate exam, and it all comes down to a single spectrum from full control to full abstraction. So far, we've built the network with the VPC, subnets, and routing. We've locked down security with IAM and firewalls. And we've made the data layer resilient with multi-Z and disaster recovery. Now we drop the actual compute inside that network. And the decision word you've seen again and again comes back to haunt this whole topic: least operational overhead. Before we get into the mechanics, 5 terms anchor everything in this episode. An EC2 Instance Family groups instance types around a single resource strength, compute, memory storage, or general balance. Amazon Web Services Lambda is fully managed, event-driven serverless compute. Your code runs on demand, no servers involved, with a hard ceiling of 15 minutes per invocation. Amazon Web Services Fargate brings that same serverless idea to containers, running your tasks without you touching any underlying cluster. The ECS launch type is the choice that sits underneath those containers: Serverless Fargate, or EC2 instances you register and manage yourself. Finally, a placement group tells EC2 how to position your instances on physical hardware, either packed close together for low latency or spread apart for fault isolation. Here's the mental shift that makes this whole topic click. Amazon Web Services compute isn't a random pile of services you memorize one by one. It's a single spectrum. At one end, you have maximum control. You own the operating system, the patching, the scaling, and the capacity planning. At the other end, you have maximum abstraction. Amazon Web Services runs everything, and you just hand over code. Every step you take toward that abstract end trades away control in exchange for less operational burden. That one axis answers most of the exam's compute questions. Think of it as 3 ways to have a roof over your head. EC2 is buying a house, total control over every room, but you own the plumbing, the roof, and the electrical panel. Fargate is renting an apartment. Someone else maintains the building and the utilities, and you just furnish your unit however you like. And Lambda is staying in a hotel. You show up, use the room for your stay, and leave. The hotel handles everything, and you never carry a key between visits. That hotel checkout, by the way, comes after 15 minutes. Here's that spectrum drawn out. On the left sits EC2, full operating system control, any runtime, any workload duration, but you patch and scale it yourself. In the middle sits Fargate. You run containers, but there's no cluster to manage. And on the right sits Lambda, event-driven, scales all the way down to 0, but with that 15-minute ceiling on every run. Notice the trade never disappears. As you move right, overhead drops, and so does control. Your job on any question is to find where the workload belongs on this line. When a question says least operational overhead, it isn't vague marketing language. It means something concrete. No operating system to patch, no cluster to size and pack, no idle capacity you're paying for while nothing runs. Every time you see that phrase, the question is really asking where the workload sits on the spectrum. And it usually wants you to slide as far toward the managed end as the workload's constraints will allow. Let's start at the control end with EC2, and the key skill here is matching an instance family to a workload. Every family optimizes one resource dimension. General purpose, the M&T families, balances compute, memory, and networking for everyday web tiers. Compute optimized, the C family, gives you the most virtual CPU per dollar. Memory optimized, RX and U, packs a high ratio of RAM to virtual CPU for in-memory workloads. And storage optimized, the I and D families, delivers high input-output operations per second from local NVMe drives attached right to the host. Picture a motor pool. The M family is a mid-sized sedan, balanced and practical for everyday driving. The C family is a sports car, built for raw speed, which here means CPU, at the cost of cargo room. The R family is a moving van, vast cargo space for hauling large datasets in memory. And the I family is a delivery truck with a specialized hold, optimized for high-frequency loading and unloading, which is disk operations per second. You wouldn't haul furniture in a sports car, and you wouldn't race a moving van. Pick the vehicle for the job. So here's the mapping you carry into the exam. A balanced web tier goes to the N family. Batch encoding or high-performance computing, where CPU is the constraint, goes to the C family. An in-memory database like Redis or SAP HANA, that's an in-memory analytics platform, goes to the R or X family. A NoSQL store demanding high operations per second goes to the I family. And a cheap, spiky development box goes to the T family. The trick is always the same. Read the description, find the resource that's the bottleneck, then map it to the family. Don't pick out of habit. T instances are burstable. While they sit idle, they earn CPU credits, and they spend those credits to burst above a low baseline when work arrives. That makes them cheap and well-suited for spiky low-average workloads, a development server, a light web app. But if the credits run out under sustained load, a T instance throttles hard, or in unlimited mode, it quietly bills you overage. Anything with steady, consistently high CPU does not belong on a T instance. That's a C family job. Amazon Web Services puts the general purpose case plainly. General purpose instances provide a balance of compute, memory, and networking resources, ideal for applications that use those resources in equal proportions, like web servers and code repositories. That's the signal to watch for. When nothing in the description screams CPU bound or memory hungry or disk heavy, the balanced M family is your default. It's the answer when the workload doesn't lean hard in any single direction. Quick recap on families. Always identify the dominant bottleneck resource first, then map it to the family letter. Never pick out of habit. And watch for the mismatch. Put a memory-hungry workload on a C instance because it has more raw virtual CPUs, and you'll starve it of RAM while paying for compute it doesn't need. Profile the workload, find the constraint, then choose. Now jump to the far end of the spectrum, Lambda. Lambda is compute that wakes up on an event. You upload your code, attach a trigger, an S3 upload, an API call, an SQS message, a schedule, and that's it. Amazon Web Services provisions the execution environment on demand and scales it out concurrently as events pour in. You build in milliseconds, and when nothing is happening, it scales to 0 and costs you nothing. There are no servers to patch and no capacity to plan. That's why Lambda is the canonical least overhead answer for short, event-driven work. Think of Lambda like a vending machine. You drop in a coin, that's the event. The machine dispenses a snack, which is your function running, and then it goes idle again at 0 cost until the next customer. You never pay for the machine just sitting in the hallway between purchases. EC2, by contrast, is like hiring a full-time cafeteria worker who's on the clock whether or not anyone orders lunch. For bursty, event-driven traffic, that difference is the whole economic argument. Here's the constraint that decides so many questions, straight from the docs. Lambda is designed for short-lived compute tasks that do not retain or rely upon state between invocations. Code can run for up to 15 minutes in a single invocation, and a single function can use up to 10,240 megabytes of memory. Read that 15-minute number carefully, because it's a hard wall. When the runtime hits it, Lambda terminates the function and marks the invocation failed. And here's the nuance people miss. 15 minutes is a hard ceiling, not a target. Lambda is architected for short, bursty, event-driven work. The closer your function runs to milliseconds, the more economically it shines compared to always-on alternatives. So the moment a scenario tells you a task runs 20 minutes, 30 minutes, or up to several hours, Lambda is disqualified outright. No workaround needed to spot it. Anything approaching that 15-minute ceiling is a signal to reconsider whether Lambda is the right fit at all. Two more things worth knowing about Lambda. First, there's only one dial. Lambda has no separate CPU setting. CPU scales proportionally with the memory you allocate. At 1,769 megabytes, you get one full virtual CPU. At the 10,240 megabyte maximum, you get roughly 6. So if you need more compute, you raise memory, which also raises costs, even if you didn't actually need the extra RAM. Second, cold starts. When Lambda spins up a brand new environment, that initialization adds latency. For latency-sensitive functions, snap start or provisioned concurrency keep environments warm to blunt it. There's a common mistake when teams move a monolith to Lambda and Amazon Web Services flags it directly. The Lambda monolith. That's cramming the entire application into one giant function behind every API route. The package gets huge, which slows cold starts. The IAM role has to be broad enough for everything, which is a security risk. And every change becomes an all-or-nothing deployment. The right pattern is the opposite. One function per narrow, well-defined task. Small packages, fast starts, a least privilege role each, and deployments you can ship independently. That maps perfectly onto MegaCorp splitting its Java monolith into microservices. Quick recap on Lambda. When the workload is event-driven, short, and stateless, Lambda is the least overhead answer for that exact shape. The hard 15-minute wall rules out anything long-running. And the economics are unbeatable for bursty traffic, because it scales to 0 and bills per millisecond. Keep that shape in your head. Event, short, stateless, and Lambda questions become easy to spot. Now the middle of the spectrum, containers. And the single thing that untangles container questions is realizing there are two separate, independent choices. The first choice is orchestration, the brain that schedules your containers. That's either ECS, which is Amazon Web Services native with no control plane fee, or EKS, which is managed Kubernetes at roughly $72 a month per cluster. The second completely separate choice is compute. Who owns the capacity underneath? That's either Fargate, where there's no cluster to manage, or the EC2 launch type, where you register and own the instances. And here's the key. Either orchestrator can run on either compute layer. Here's exactly what Fargate takes off your plate, in Amazon Web Services' own words. With Fargate, you no longer have to provision, configure, or scale clusters of virtual machines to run containers. This removes the need to choose server types, decide when to scale your clusters, or optimize cluster packing. That last phrase, cluster packing, is the tedious puzzle of fitting the right number of containers onto the right number of instances. Fargate makes that puzzle disappear entirely, and critically, unlike Lambda, Fargate has no execution time limit. So when do you pick each compute layer? Fargate means no cluster, no machine image, no packing. and each task gets its own isolated kernel. It costs more per task, but teams ship faster because there's nothing to manage and there's no time limit on the task. The catch: Fargate has no GPU support. The EC2 launch type flips that. You register and manage the instances yourself, which gives you full control over instance type, GPU access, and kernel tuning, and it gets cheaper at large steady scale. But you own the capacity provisioning. So the rule is simple: reach for Fargate for least overhead, and drop to the EC2 launch type only when you need GPS, specific tuning, or the economics of hundreds of always-on tasks. For the orchestrator choice, really only one scenario decides it. ECS is Amazon Web Services proprietary, uses JSON task definitions, and carries no control plane charge. EKS is managed Kubernetes, the full Kubernetes API, and it charges about 10 cents an hour per cluster, roughly $72 a month. So here's the decision rule. Choose EKS only when Kubernetes or multi-cloud portability is an explicit stated requirement. If the scenario never mentions Kubernetes, ECS is the lower overhead and lower cost answer. Don't reach for EKS just because it sounds more powerful. Back to EC2 for one last topic that shows up reliably: placement groups. A placement group tells Amazon Web Services how to position your instances on the physical hardware. There are 3 types. Cluster packs instances close together for low latency, high throughput networking. Spread forces each instance onto distinct racks for maximum fault isolation. And partition splits instances across separate rack sets, built for large, replicated, distributed systems. We'll take them one at a time. Picture seating an orchestra. For a cluster group, you seat every musician at one table so they can whisper cues instantly. Maximum coordination, but if that table collapses, the whole ensemble goes down together. For a spread group, you put each musician at a completely separate table. So one spilled coffee only affects that one player, maximum isolation, but you're capped on seats per room. For a partition group, you group by section, brass, woodwinds, strings at separate tables. Players share a desk within their section, but no section shares hardware with another. That gives you fault isolation that scales to hundreds of players. Amazon Web Services describes them crisply. Cluster packs instances close together inside a single availability zone, enabling the low latency network performance needed for tightly coupled node-to-node communication, typical of high-performance computing, or HPC. Partition spreads instances across logical partitions so that groups in one partition don't share hardware with another. The strategy for large distributed workloads like Hadoop, Cassandra, and Kafka. And spread strictly places a small group of instances across distinct hardware to reduce correlated failures. 3 types, 3 very different jobs. Here they are side by side with the keyword that triggers each one. Cluster puts instances on the same rack for low latency. That's your signal for high-performance computing and tightly coupled message passing interface, or MPI workloads. And remember, it lives in a single availability zone only. Spread puts each instance on a distinct rack, capped at 7 per zone. That's your signal for a small number of critical instances, like a primary and standby database pair. And partition uses separate rack sets and is replica aware. That's your signal for Kafka, Cassandra, and Hadoop, the big distributed systems that replicate data across nodes. 2 numbers worth memorizing. A spread placement group supports a maximum of 7 running instances per availability zone. And a partition placement group supports a maximum of 7 partitions per availability zone. Watch the difference carefully. Spread caps instances, partition caps partitions, but each partition can hold hundreds of instances. So if a scenario describes 10 or 12 instances that all need hardware isolation, spread can't do it. That's a partition job. A few placement group constraints worth internalizing. First, a cluster group cannot span availability zones. Low latency networking and multi-AZ resilience are a contradiction. You cannot get both from a single cluster group. Second, launching all your cluster instances in a single API call reduces the risk of an insufficient capacity error, since Amazon Web Services tries to reserve contiguous hardware in one shot. Third, if you need more than 7 isolated instances, that's partition, not spread. And finally, because cluster instances share a rack, one hardware failure can take the entire group down at once. Let's tie the whole spectrum into one decision flow with 3 gates. Gate 1. Does the workload need operating system control or a GPU? If yes, it's EC2, full stop. Gate 2. Is it containerized and long-running? If yes, it's Fargate for least overhead. Gate 3. Is it event-driven and short? Under 15 minutes? If yes, it's Lambda. Work through those gates in order, and only after you've landed on a service do you start comparing pricing. That sequence keeps you from getting seduced by the word serverless before you've checked the constraints. Watch how MegaCorp's monolith splits across all 3 homes using exactly that flow. The sub-second API handler that answers HTTP requests goes to Lambda behind API gateway. Event-driven, short, scales to 0. The daily batch transform that takes 25 minutes can't use Lambda because of the 15-minute wall. So it runs as a Fargate task fired by an event bridge schedule. Managed containers, no time limit, no instances to own. And the legacy service that needs a custom JVM tuning flag and a specific kernel parameter needs OS control. So it lands on EC2 on an M or C family instance inside an autoscaling group. One monolith, 3 different answers, each driven by the workload's shape. 2 conflations trip up even experienced engineers. First, serverless does not automatically mean Lambda. Fargate is serverless too, no servers to manage, so a serverless question about long-running containers points to Fargate, not Lambda. Second, containers does not automatically mean EKS, unless Kubernetes is explicitly required. ECS is the lower overhead answer. Both of these come from reading the label instead of reading the workload. Start every compute question with duration and trigger shape, not with the buzzword. Let's carry these rules forward. Compute is one spectrum, EC2 for control, Fargate in the middle, Lambda for maximum abstraction. Least operational overhead pushes you toward the serverless end, unless a hard constraint pushes back. Lambda's 15-minute ceiling eliminates it for long jobs, while Fargate has no such limit. Fargate removes cluster management. The EC2 launch type keeps that management when you need GPS or large-scale economics. For placement groups, cluster means low latency, spread means 7 isolated instances, partition means big replicated systems like Kafka. And notice we never touch spot, reserved instances, or savings plans. Those purchasing options are a cost domain topic we cover later in the course. Now let's see how well all of this stuck with a quick 5-question quiz. Let's test what you've learned. Question 1. A daily data transformation job runs for about 25 minutes processing a large file. The team wants the least operational overhead and doesn't want to manage servers. Which compute option fits? Is it A, Lambda triggered by an S3 upload, B, an EC2 instance in an auto-scaling group running the job on a schedule, C, a Fargate task triggered by an event bridge schedule, or D, a Lambda function chained through step functions to extend runtime? Run the decision rule from earlier before you answer. This one is C. The 25-minute runtime blows past Lambda's hard 15-minute ceiling, which rules out both Lambda answers, including the step functions workaround. Fargate runs the container with no cluster to manage and no time limit, so it's the least overhead fit. Question 2. An application resizes images the instant they're uploaded to S3. Each resize finishes in about 800 milliseconds, and traffic swings from near zero at night to thousands of concurrent uploads during flash sales. Which service minimizes cost and operational overhead? A. Lambda invoked by the S3 upload event. B. A fixed fleet of EC2 instances sized for peak load. C. A Fargate service kept running continuously behind a queue. Or D. An EKS cluster with the Kubernetes horizontal pod autoscaler. Pause here if you want more time. The right call here is A. The work is event-driven, well under a second, and wildly bursty. Lambda scales from 0 to thousands of concurrent runs automatically and bills only for execution time. A fixed EC2 fleet and an always-on Fargate service both burn money at idle, and EKS adds Kubernetes management you don't need here. Question 3. A streaming platform runs 300 Kafka broker nodes that replicate topic partitions and must guarantee that a single physical rack failure cannot destroy all replicas of any partition. Which placement strategy fits? A cluster placement group for low internode latency. B. A spread placement group across distinct racks. C. A partition placement group with rack-aware replication. Or D. Multiple cluster placement groups, one per availability zone. Think about which constraint matters most here. It has to be C, and here's why. Spread caps out at 7 instances per zone, nowhere near 300 brokers. A partition placement group places instances in separate rack sets and exposes partition metadata so Kafka can do rack-aware replication. That's exactly the design intent for Kafka, Cassandra, and Hadoop. Question 4. A team is deploying containerized microservices. The scenario mentions no Kubernetes requirement and no need for multi-cloud portability, and cost optimization is a stated priority. Which orchestrator and compute combination is most appropriate? A. EKS on the EC2 launch type for full control. B. EKS on Fargate to avoid node management. C. CS on Fargate for Amazon Web Services native orchestration with no cluster to manage. Or D. ECS on the EC2 launch type with a self-managed auto-scaling group. Lock in your answer before I give it away. The answer is C. With no Kubernetes requirement stated, EKS only adds a control plane charge and Kubernetes operational surface you don't need. ECS carries no control plane fee, and putting it on Fargate removes cluster management entirely. That's the lowest overhead, lowest cost combination for this scenario. Last one. A solutions architect needs to run a tightly coupled scientific simulation across 16 EC2 instances that must exchange data at the lowest possible latency. The simulation runs for several hours on a predictable weekly schedule. Which placement group type is correct? And what constraint must the architect be aware of? A. Spread placement group supports up to 16 instances per availability zone with hardware isolation. B. Partition placement group. Place each instance in its own partition to guarantee no shared hardware. C. Cluster placement group. Instances are placed on the same rack for low latency networking, but the group cannot span availability zones. Or D. No placement group needed. Enhanced networking on modern instance types provides sufficient latency reduction. Run the decision rule from earlier before you answer. It has to be C, and here's why. Tightly coupled workloads that need minimum latency are exactly what cluster placement groups exist for. Same rack, lowest possible network delay. The constraint is that cluster groups are confined to a single availability zone. Spread is disqualified because it caps at 7 instances per zone, and partition is designed for replica-aware distributed systems, not low latency coupling. That closes out elastic compute, EC2, Lambda, and Fargate. If this earned a place in your study plan, subscribing keeps the rest of the Cloud Architect path coming and helps it reach new students. Drop a comment on what surprised you most. If you'd like a series on a different certification, name it below. And if the pacing or the visuals could improve, I want that feedback. See you next time.